Welcome to Math 31. This is the lesson on the area problem. So the area problem is where we start linking what we know about antiderivatives to a whole new sort of geometric issue. Now, taking this back, a bit of a history lesson, there are two main problems of calculus. The first one we've worked with before, which is the slope of the tangent to a curve. So this is what we concentrated on for the first few months of this course, where you'll be given a function and you'll want to find out the slope at any point along that curve. Now not we didn't, but somebody figured out a way to determine what the slope was of the tangent line to a curve, and we were able to use that. And very useful, very helpful, any sort of slope or related rate questions or rate of change questions. But the second question is different, and it's the area under a curve. And it's similar in a sense, because if you take a look at this diagram in front of us, and I've shaded in an area between, well, it looks 2 to 5 sort of thing. And it's difficult to accurately measure what the area is underneath that curve from the x-axis, above the x-axis and below the curve, or for that matter, below the x-axis and above the curve, or whichever, or between two curves, because we're really limited in our ability to determine area. Now, of course, if you had a simple graph like a linear function such as this, and then you were asked to find the area from 0 to 2, now that's not a big deal. Now, of course, be a straight line. If everything was linear or just even straight lines, shapes that had the straight lines in them, it wouldn't be a difficult thing. Because if you were going to get the area here, in general, we would say area is equal to 1/2 base times height, because it is a triangle. So in this case, let's even work it out. The area is equal to 1/2. The base is 2. And the height, you can either do it by inspection of the graph itself or just by working with f at x is equal to 2x. And 2 times 2 is 4. So all is said and done, we get area is equal to 4 square units. Now if we generalized a little bit, we might say something like this, that the area is equal to, or as a function of x, is equal to 1/2 times the x value, so in this case x is 2, multiplied by f at x. Because the y value is always going to be, for all of these, the y value will be f at x. So that will work. Now where things get complicated, as we saw in the previous illustration, is where you do not have a linear function. So if you were just going to look at a quadratic, a simple quadratic like this, f at x is equal to x squared, and somebody wanted you to get the approximate area from 0 to 2, then we've got a problem. Now if the curve is linear-like, you can do a real rough approximation like that, but you know that it's an approximation. You know it's not going to be too accurate. So what they figured way back when was that there's two sort of good approximation methods, Armstrong methods, not quick or easy. But one thing you could do is, if you were going to approximate the area, is you could draw a series of inscribed rectangles. Now, inscribed rectangles would be something like this. Now, I've just really roughly drawn them in, and you can see that it's not perfect because of the gaps that you've got between them. But the thinking is pretty, reasonable. Because we can handle the area of a rectangle, if we put in a series of rectangles inside, underneath the curve like this, inscribed, then we could get an approximation. And you're already probably thinking, well, by putting more and more of them in, we could get a better and better approximation. So if you check these ones out carefully, there's actually supposed to be 10. I'm not sure I got them all in there right. But it's not a perfect one. Now, they're supposed to be the same size, too, the same width, which I guess they kind of are. But there's a problem. There's a few little gaps in there. And notice in this case that the left corner, they're inscribed, so they're inside this. The left corner of the rectangle is touching the curve. Now this would be an under approximation. It may be fairly good, but it still is an under approximation. We would expect the true answer to be somewhat more than what we get. Then take a look at the next one. Here we have circumscribed rectangles. So draw the picture again, and in this case you see that the upper right corner is touching the curve, or it looks that way, at least the ones we can see. And this one here looks like it's a little bit big, but that's no big deal. This is an over approximation. So you're probably already thinking, well, you take the under approximation, you take the over approximation, and average the two. And in fact, you'll get a pretty good answer as a result of that. Now, we're going to do better than that, though, or we're actually going to take this and calculate it and work it out. So you're going to see that this is a fairly lengthy process. It's really not that good of a method. It's accurate, but it's definitely time-consuming, and it's also this is an easy equation. A quadratic centered with its vertex at the origin is really just a short step up from a linear function. But let us approximate using inscribed triangles first off. Now, what I've got is I broke this into intervals. And I'm going to break specifically into 10 intervals. Now, you know and I know that the more intervals we have, the better in terms of accuracy. But because this is mostly to illustrate a point, I'm not going to worry about it too much. Because as you probably figured, we're going to develop a better method down the road. Now, if we break into 10 intervals, each interval is going to be, well, 2, because that's how far we're going. Each interval will be 2 divided by 10. So that's going to be 0.2. So that'll be the width of each one of them. The height, or length, if you prefer, of the rectangle will vary. And it tells us then, just to really be as careful as we can, .4, 0.6, 0.8, there we are. So I'm actually not right on with this, so we'll have to just use the graph as a guide for this. But the intervals themselves then shouldn't be a problem. Are going to be 0 to 0.2. The next one is going to be 0.2 to 0.4, etc. And then the very last one is going to be 1.8 to 2. So each interval has a width of that. So this is 1.8, this is 0.2, etc. like that. You could fill them in if you wanted. Now the height, because it's inscribed, the height or the length in more standard rectangle form is at the left endpoint. So this means that in each case, if we're trying to work out the height or the length of the rectangle, it's the left endpoint of the interval that we're concerned with. And, you know, the idea really is that we're trying to get a formula so that we can calculate the area of each one of those. So I'm going to get a little bit more space to work, and then let's see where this takes us. So if we listed all of these, the first interval is going from 0 to 0.2. I won't list them all, but I'm going to list enough so that we can see what's going on. Then the next one is going to be from 0.2 to 0.4. And then I'll do one more here, 0.4 to 0.6. And then finally to 1.8 to 2. Now, for each of these, the width and then the length or height, if you preferred, the width is always going to be 0.2. And that's true for each of these. So that doesn't change. They're 10 equal intervals. So that's part of our rectangle. 0.2. The interesting thing is the height, or the length. Now, because it's the left endpoint, just to go back for a sec, it means that even for this very last point, the y-coordinate is f at 1.8. And then the very first one is f at 0. So that's the way it works. It's always the left point for the interval. So it means, for the first one, we would go f at 0. Then the second one would be f at 0.2, so always the left limit. Then the next one is f at 0.4. And then the very last one is f at 1.8. Now this matters quite a bit. So using the area formula, which is equal to L times W, and keeping in mind that we want to add all these together, the approximate area is going to be equal to, for the first little rectangle, would be a width of 0.2. I'll put that one first, multiplied by f at 0. And then the next one would be 0.2 again for the width, multiplied by f at 0.2. And then so on like that, 0.2 multiplied by f at 0.4. And then finally, well, all of these ones, 0.2 multiplied by f at 1.8. Now we do have a formula for these, so I think we have to remember that the formula or the equation is y is equal to x squared. So don't forget that. So recall the function itself is f at x is equal to x squared. So what it means is that this very first one is going to be 0, because f at 0 squared is going to be 0. So we actually lose the first rectangle, which means we now only have 9 instead of 10. So moving on, the area is going to be equal to, well, 0, but the first real one is going to be 0.2, and that's going to be there, multiplied by the 0.2 squared, because we sub in the x value into the formula, into x squared, we get that. And then the next one is 0.2 again times 0.4 squared, which is that, and then all the way down the line until we get to 0.2 multiplied by 1.8 squared. But we only have 9 of them. Now this, if we were trying to simplify this, we may well decide there's a common factor of 0.2 for each of them. So I'm going to factor out that 0.2. So area is equal to, factor that out, and that leaves me with 0.2 squared plus 0.4 squared plus all of these to 1.8 squared. Now here's where we have to change the way we think and introduce something new. If you think back to the previous lesson on sigma notation, you'll recall that sigma notation allows us to work out repeated sums like this as long as there's a formula. And if we do set up as a sigma, we need that formula. And the formula would go like this. We can see that, first off, using this, area is equal to sigma, starting at, let's say, I is equal to 1. Doesn't matter which variable you use. And up to 9, because we have 9 terms. Remember, the 0 went away. We do have 0.2 because that 0.2 has been removed as a common factor. But the formula, if we call this I is equal to 1 and I is equal to 2, to keep the counting numbers going, what in fact we're getting is a formula where we have 0.2 times I squared. So you can check that out. If you were to take like I equal 1, okay, that makes sense. And then I equal 2 should also make sense. So 2 times 0.2 is going to be 0.4. So we do get the second term. And so I is equal to 3, and then so on like that. So whatever the I value is, you can just straight work it out.